Hi, welcome to Mat210, graphing using derivatives. Chapter 2 deals with applications, and this is one application, graphing using derivatives 2.1, 2.2 do it. Now, we could graph on a graphing calculator, but that wouldn't be any fun, would it? So we're going to use our first derivatives and things like that. Before graphing calculators, we used to have to do this by hand, and sometimes it was kind of difficult to do. Two key things about graphing with derivatives, first derivatives. The first thing is that we pick points in which the slope is 0 or does not exist. Let me show you. Say we had a graph like this. At this high point right here, the slope would be 0. And this is what we call a critical point. We want to use this for our first derivative. We're going to use our first derivative when it's 0. Here's another indication that it would be 0. Maybe this goes up really straight, like that, and that curves. And this would be a point at which, right here, and it might be even steeper than that, obviously, the slope does not exist. That's another key point in which we will graph. We will use the first derivative to help us graph. So these are key points, like this is what sometimes we call a relative max, a relative min, a critical point where there is no slope, and a couple other critical points would be something where it kind of jogs off and then goes into a curve, not a gradual curve, but a steep curve. Slope does not exist at that point. Or if it comes to a point and then curves again, you might find that the slope is 0 or does not exist at that point. So those are key points at which we can use. These become what we call critical points. The other thing about graphing with the first derivative is when we take the first derivative of some problem, let's call it C. We take the first derivative. If it's positive, in other words, if it's greater than 0, then we know that the function is increasing. Right here would be probably slope is 0. And then when it's coming down here at the first derivative is less than 0, in other words, it's a negative number, and it's decreasing. So we can identify areas where it's increasing and decreasing. And this helps us identify these critical points. So this would be a positive increase. So what we're going to be doing is looking for these critical points where the slope is, the first derivative is 0, or where the first derivative does not exist. Mostly when it's 0, but sometimes when it does not exist, we'll look for those points too. So that's the key to graphing, is knowing those points. So let's take the first example in the book, and I'll help you out, and we'll kind of work our way through this mess. Okay, there's quite a few steps involved. So this is on page 204, the first example. Now, we could just make a series of points and plot this curve, or we could use our graphing calculator, but we're going to try to make a sketch. So this is not a real perfect graph. It's just kind of a, let's see if I can focus this a little bit better. It's just kind of a, oh, that ain't doing much. Okay, it's just a way to help us make a little bit, kind of get an observation of it. So we're going to start out with this problem right here. This is our problem. F of x, I was trying to find the problem, equals 2x cubed, pretty long one, minus 3x squared, minus 12x plus 12. Now in the book they made a table of values. We're not going to make a table of values for this. We're just going to graph the way it is. I don't know, it just doesn't seem very, see, that focuses it in better. Okay, so the first thing we want to do is take the first derivative of this function. So that would be 6x squared minus 6x minus 12, right? So we take the first derivative. Then, because the first derivative actually represents the slope of this graph, that's what the first derivative is. It's the slope of this graph. We want to see what happens when the slope is equal to 0. So we're setting this equal to 0. So remember, the first derivative is a formula for the slope of a function. Okay, I didn't understand it either when I was in school, but that's the way it is. So let's factor this out. We're going to take out a 6, right? And then we're going to still equal to 0. We don't really need this 6. It's extraneous. So now we're going to factor this down using some of your algebra, x, and factor down the 2, and we get 1 and 2, and play around with our signs, negative and positive. So we factored it out. Then we're going to solve this. X plus 1 equals 0, x minus 2 equals 0. So we'll put a 1 in here, and bring the 1 to the other side. X is negative 1. Take it ahead here. And bring the 2 over. X is 2. So these are what we call our critical points. These are the points at which the slope is equal to 0. Those become our critical points. Okay, another thing, what I like to do at this point is try to find y, the y values that correspond to these x values. And the way I do that, to find the y values, we always go into the original problem. That's very important. Don't go into your derivative or you come up with wrong numbers. So we want to put a negative 1 into the first derivative. We can see that, okay. So I'm putting in, not into the first derivative, into the original problem. Very important. And this will give us our y value for negative 1, and we can just calculate that out. Let's see. Now remember, don't multiply these together. Do the power first and then multiply. So this will be negative 2 minus, this will be a 1 times negative 3 is negative 3 minus plus 12. So that looks like it's 24, take away 5 is 19. So when x is negative 1, y is 19. I like to get that out of the way first. Sometimes you can do this at the end. It doesn't matter, but usually to me it's easier to do it at the beginning. Now let's put a 2 into the original problem. Okay, we're going to go through this kind of fast. That'll be 8 times 2 is 16. 4 times 3 is 12. Minus 24 plus 12. So we see these cancel out. It'd be a negative 24 plus 16 is what? 8. Negative 8. Yeah, those look like they're correct. I just double checking my work. Okay, so now we got our critical points. Now we're going to make a table to help us with these critical points. And this is where we're going to see if our first derivative is increasing or decreasing. So we just want the x value on this line, and we're not going to use those. Don't ever use these actual points. Don't substitute those into the first derivative or anything like that. This was a 2. All right. Now, what we're going to do is we're going to take test points from these areas, and we're going to test them to see if they come out positive or negative. And then it tells us if our first derivative is working. But we're going to take that and put it into our first derivative. Now you could put it into this equation or this one. I'm just going to put it into the original one. So I'm going to put it over here called test points. Okay, and I'm going to use the point 0 because that's, wait, I want a number less than -1. I'm going to use a -2. Then I'm going to use a number in this interval. I could even write it down here if I want 0, just write it real small. And maybe in here we'll put a 3, some kind of number. So I'll put them a little bit bigger here so you can see. So I'm just putting those into this first derivative, into f prime, very important, equals. So we're going to go with 6 times -2 squared minus 6 times -2 minus 12. And I think I worked this out. Let's say I got 36 minus 12. This should come out to like 24. So we see that this is a positive number. So I'm going to put a plus here, and that tells me over this interval that this function is increasing. There's an increase. Now I'm going to put a 0 in here, see what happens. Replacing this function x with a 0, but I'm doing the first derivative. So 6 times 0 squared minus 6 times 0, that should zeros, minus 12 equals -12. So we see that this is a negative, and that means it's decreasing. Now remember, we're just making a sketch. And now I'm going to put in a 3 and see what happens. Into the first derivative, into this problem right here. I don't know if I worked this one out, 54 minus 18 minus 12. I think it comes out to 24, but I'm not positive, but it does come out positive. And that's what I'm concerned. I'm not really concerned with these numbers. I'm concerned with the sign of these numbers. The number really doesn't matter. It's the sign. Okay, so that's plus, that's an increase. So now I'm ready to actually do the problem. I'm ready to graph this thing. I got all the information I need. I know my critical points right here. And I know what's happening around them. So let's make a sketch here. And this is just a preliminary sketch. I could be more fancy, but at -1, I see this is way up here in 19. And down here, let's see at 2, it's down here, not quite as far, at -8. 2 comma -8. So I see my 2 points. Now, let's see what happened. Just before it hit the number -1 right here, it was increasing. It was starting up from -infinity and it was increasing to that point. Then, right after that point, it started to decrease down to this point. Kind of a crude sketch. It probably should be better. And then at this point, I see it's increasing again. So this is not as good as the one in the book, but it gives me an idea of what's happening here. Here it was positive, it was increasing, the first derivative was increasing over this interval. It was decreasing here. It was negative. And then finally over here, it's increasing again. It's increasing. So increase, decrease. Now, this point right here, because this is going to keep on going up, this is going to keep on going down. This is what we call, this kind of peaks out right here, but we call this a relative max. maximum. And this point is about as low as it's going to, it's relatively low. It's going to go lower if we hit infinity, but this is a relative, abbreviate, minimum. So those are your two. The relative min is 2, -8. The relative max is -119. Pretty terrific, huh? And we've gone through. So quite a few little steps. Number one, let's review. Number one was to find a first derivative. Number two was to set it equal to 0 and solve it. So we solved that. Number three, I found the y values that were associated with the first derivative because that makes it easier to plot. And we put those into the original problem, the original crispy formula. Because I know when I first started doing this, I used to put them into the first derivative and things came crazy and you go nuts. Step number three, I wrote these down and then I developed some what we would, this is step number four, some test points. And I tested out those points. I just randomly picked numbers in these intervals and I tested them. And then step number five was I graphed the information I had when it was increasing. I hit my two key points and then I built around them to get the idea of what this curve is, you know. So, you know, you might even make it a, you know, like V's, but you want a little curve to it. All right, we'll try one more and see if we can do it. Here's the second problem. This is kind of an interesting problem. Function of x, or you could say y, it doesn't matter, equals 2x cubed minus x to the fourth. Still kind of blurry. I didn't know that. Maybe it's my eyes. There we go. Maybe it's my eyes. I don't know. Okay. So what was our first step? Take the derivative. That gave me 6x squared minus 4x cubed. Then the second step was to set this equal to 0 and factor it. Because that's remember when the slope is equal to 0, that's when we're going to get those critical points. So let's factor. Let's see, we could take out a 2x squared even. So that gives me 3x minus 2x. No, it gives me 3 minus 2x. There we go. All right, now I'm going to factor those down. 2x squared equals 0. Well, only thing that would work is a 0 to solve that. So x is 0. It's one of the critical points. And then we'll put in 3 minus 2x equals 0. Negative 2x equals negative 3. Divide by negative 2. Watch your signs because this is real. These are very important points. If your sign is messed up, obviously the whole thing goes downhill. So that's 3/2. Or if you wanted to use a decimal, I guess you could use 1.5 if you wanted. If you don't like, oh, hey, this is terrible. I wasn't even looking at that. All right. Or 1.5. But anyhow, we solved them. You should know how to do that from your algebra. Now, what's the next thing we were trying to do? After we solved it, we tried to find out y values. You can put that anywhere you want, y values. And we go to the original problem. All right. So here we got y equals 2x cubed minus x to the fourth. We're going to put in a 0. And we see that's 0, okay. So we know that the y value is 0, this will be 0.00. Then we put in, I used that 1/2 in here. And I got y equals, well, I put in 3/2, 2 times 3/2 squared minus 3/2 to the 4th. And I got something like 2 times 27/8 minus 81/16. And I multiply that out and put it over 16. And I got 108/16 minus 81/16. And it ended up 27/16, or 1 9/16. And this was 1.5 or 1.5. Okay, so we got our key points. Now, so let's see what happens with those critical points. I don't know how big you have to make this. Don't substitute these in. Pick numbers in these restricted areas. So I went ahead and picked a -2. These are my test points. Sometimes we call them TPE, test points. And we put those into the first derivative. And I got 6 times -2 squared minus 4 times -2 cubed. Put them into this problem right here. And what happened is, after I worked that out, I got 57. So that's the key right here, is it came out positive. And so I know this is an increase. Okay, then I picked a number between 0 and 9/16. I just picked 1. Worked it out. This one a little bit easier to work out. I got 6 minus 4. I got a 2, which was also positive. So it's still increasing. And we'll explain what that means in a minute. So you might have thought, well, okay, they go plus, minus, plus, But this one didn't. Kind of interesting. Okay. So then I put in here, let's see, and this one I put in a -2, and then I put a 1. Then I used a +2. You got to make sure the number's in that interval. You can't just randomly pick a number. This one came out to be a -8. So I saw it was negative, which meant it's decreasing. So now I'm ready to graph. I did step 1, step 2, solved it. Step 3, I found my y values. I got this point 0, 0. I got this point 1.5, 1 9/16. And then I tested those intervals, because right here, this is when the slope was 0 at these key points. So I don't want to use those. I want to use numbers in between. Anyhow, let's see what the graph comes out to look like, x and y. So I have the point 0, 0. And I have the point 1 9/16. I mean, when I put 1 9/16, I should have put 1.5, but it wouldn't make much difference, because 9/16 is pretty much a half. I should have used my x value and not my y value, which in this case I was lucky because they were about the same. So this would be 1.5. Let's make some divisions here. 1.5, and it goes up 1 9/16, which is pretty close to 1.5 too. All right. So what's happening here? It said from here to here, it said it was increasing when it hit this point. But when it hit that point, it said instead of turning down like we probably figured it would do, it increased some more. And then when it hit this point, then it decreased. So the graph looks sort of like this. It's increasing and still kind of increasing and then coming down. Increase, increase again, and then decrease. Interesting, huh? So that was kind of an interesting little curve. Now, this point right here would be your relative min, but we can see it's actually an absolute min because it's never going to get higher than that. So we could call it also absolute min, because not min, but max, I'm sorry. Absolute max. It's not going to get any higher than that maximum point. And that occurred at the point 1.5, comma 1 9/16. At that exact point, we hit our maximum. Now, what about this point, 0, 0? And that point is called an inflection point. An inflection point is when a graph continues in the same direction but has a little kind of shifting goes on right around that point. There's a little thing, but we were going positive and we continued positive. So we were going in a positive direction and continued positive. That's called a point of inflection. So at that particular point, there is no relative max or min. At a point of inflection, no max, no min. It's just kind of a hiccup or something in the curve. Did a little minor little shift right then. Okay, so I hope this helps. I mean, you want to really try these problems and try graphing them. They can be a lot of fun. I know you can look at your graph. Well, it doesn't hurt to look at your graphing calculator and then see if you're doing it right. But you want to try some. I mean, if you can't do them all, at least try a few of these, because this is kind of the fun part of calculus is using the calculus to kind of help us in getting involved with solving the problems. You know, finding the derivative, solving the derivative, finding the related y values, making a grid and getting some test points and see what's happening on those test points. And this one threw a little curve at us, maybe a little bit. And then finally, number 5, graphing this thing. So if you do those things, kind of 5 steps, it won't be too bad. I know it's a little confusing, but okay. One reminder, when you want to find y, you go into the original problem. When you're working on these intervals, you always go into the first derivative. These are based on the first derivative, okay? So you want to make sure, don't go into the original problem and try to do these intervals, or they probably won't work either. You know, so you have to be kind of careful. The intervals, these intervals here, develop from the first derivative, f prime x, okay? And we're looking at what's happening. What's happening? Remember, f prime x is the slope. So what is the slope doing over this period of time? The slope is increasing. What's happening to the slope here? It's decreasing. Right at this key point, the slope is 0. Then it's decreasing. See? So we can kind of tell what's going on. It's a kind of exciting journey. Hope you enjoy it. And I'm sorry about that. Something about the way it's working.